actually processed this when I've said it, you are allowed to use VPython on tests. That means that you can practice doing that. Why would you want to? Because it's so much easier to do vector calculations in VPython than it is to do them on your calculator. So the time to practice is with your homework. So the easy way to do it is to just go to glowscript.org, which you've seen me using here. You can log in with a Google account, and you can write programs there. Are you going to make mistakes? Yes. Were you going to make mistakes with your calculator? Yes. But they're easier to fix in your program because once you've typed mass equals 0.43 kilograms, and then you've gone through 2 steps in iteration to solve a position update thing, and then you realize that actually the mass was 0.47 kilograms. Instead of doing every single calculation again, you just change that, rerun the program, you're done. So it's so much easier. So don't be scared. Come to office hours. James will help you. I'll help you. You gotta get your toe in, okay? But once you do, you have a beautiful written record of your work. You can see what your chain of reasoning was. You can see if there's an error, you can fix it, and you don't have to recalculate everything by pushing all those buttons again. You just rerun your calculation. So it's there to be useful. So if you're intimidated, come to office hours. Someone will gently help you get started. Yeah, you're going to make a few mistakes along the way, but I can guarantee you would have made a few mistakes with your calculator anyway. And once you get good at this, which won't take very long, you'll find that it's really a much easier way to solve these numerical heavy problems. Okay, so end of that sermon. Second point, in lab and in recitation, I've seen some of you going through your notes. Some of your notes aren't very good. Now, why are they not very good? Because they're not really organized the way you need to organize them to learn physics. So what's different about physics? Well, in some classes, if you take a biology class or something, there's really a huge amount of information, and you've got to make sure to get it all down, and you've got to learn all of it, and it's all important. Physics is really different. It's very hierarchical. There are a small number of things that are really, really, really important. And you really need to know what those really, really, really important things are, and they should be set off in your notes. So your notes shouldn't all be at the same level. You shouldn't be flipping through pages with lots of vectors and numbers and whatnot on them, looking for the momentum principle. Okay? That's really fundamental. It should be in a big red box in your notes. So let's, because the way we work in physics is the point is not to memorize every problem that you see. And it's certainly not to memorize the numbers in every problem that you see. They're just numbers. The point is to start from something fundamental and reason, figure things out, figure stuff out. So it's about reasoning. So we need to remember the really important ideas. You shouldn't actually have to look through your notes for the momentum principle, because if you don't know what it is, you can't reason with it. So the really important things, print them out in a big font on a piece of paper, tape it to your ceiling above your bed, and look at it before you go to sleep. Those are the really important things. So what are the things, the big ideas you ought to be able to find the big ideas really, really easily in your notes. Okay, and so after every lecture, during a lecture, after every recitation, doing homework, ask yourself, what are the big ideas? What am I supposed to be getting out of this? And what's details? What's just grinding through numbers? which a computer can do for you better than you can do. So what should be in our big ideas list? There's some definitions that are important because they involve quantities that we work with all the time. So what's one thing that's important? We're working with motion a lot here. The momentum principle is the most important thing ever. So and what's one way of writing it? Okay, so we can write it. One way to write it is the change in momentum of a system is equal to F net delta T.
Delta P equals I.
So delta P equals impulse. Okay, so this is the impulse. What else? We've used a different form.
P future is equal to P initial plus.
Okay, P future is equal to the momentum now plus F net delta T. This is the same equation because P future minus P now, or P final minus P initial, that's what delta T is, right? So that's not two equations, that's one equation. And you could rearrange it. Now, in order to understand that equation, we need a definition of momentum, don't we? Okay, so that's important. So what's momentum? Gamma times the mass times the velocity, which is a vector, and it's approximately equal to mv if the speed is significantly less than the speed of light. Okay, so we need that definition. What else do we need to talk about motion? The relationship between position and velocity? Right. So we have this definition of V average, which is change in position in a given time. And of course we can rewrite that as the update form. Our final is our initial plus V average delta T. Again, these are the same equation. Is there anything else so far?
The V final equals V initial plus F net over mass.
Okay, so we have an well, but it's not F net over mass, is it? What is it? So and where does that equation come from? It really is just rewriting. So if we're going to update velocity, this equation, V final is V initial plus F net over the mass delta T. That's this equation just divided by m. Right? So that's not fundamental. That's there really isn't anything else fundamental so far. That's it. Now, we're going to work on ways to calculate forces and use them. I would argue that there's one other idea that's important, and that's this iterative update of momentum in position, and where we find the net force acting on a system. So far that's been a little boring because our forces have all been constant forces, but that's about to change. And now we update momentum, and we use the new momentum to update position. And this works really well for a small enough time step. And then we just, sorry. So that process of predicting motion. Okay, we're going to be doing this all semester. So that's the fundamental stuff so far. And it should look fundamental in your notes. It should look fundamental to you. You should try to start from these ideas. And you should try to convince yourself that different ways of writing the same equation are really still the same equation. Okay, so that's really important. Questions about that? Comments about that? Yes?
So if you do it in like the program, to like create this while loop using the iterative update, like would you use while time is less than something to do that, or how would you?
It depends on how, yes. So it depends on, I mean, if you're just solving a homework problem and it says go from t equals 0 to t equals 1.5 seconds in 3 steps, then honestly, you have the option of cutting and pasting your code and not using a loop at all, but just changing, adding delta t. But in that case, I'd say while t is less than 1.51 or something like that, starting with t equals 0 and delta t is 0.5, that's what you're told to use, and then that. But there are a number of ways to do it. You could instead decide you want 3 steps. I'm going to make a counter n. I'm going to, okay, this is an easy way that we've done before. It's a good way. And yeah, the very first time you do it by yourself, it's a little scary. But you can do it. Okay? You wrote an animation last week in lab. You made something move across the screen. Okay, this is something you can do. Come and get help. We'll help you get used to it. You'll find that if you practice it and do it with your homework, you're going to get good at it, and you're going to find that this really speeds up and simplifies your life. Other questions? Okay, so far we've just had constant forces, and today we're going to talk about, I think, 2 forces that are not constant, and talk about how to calculate them. And of course, because they're not constant, once things move, you have to recalculate the forces. The first one that we're going to talk about is the force some object that's touching the spring. And then I think we'll have time to start talking about the gravitational force, which is one of the 4 fundamental forces between 2 massive bodies, but we'll see. So a spring. We don't have a spring, but we can imagine a spring here. So how do springs work? Well, the spring has some relaxed length, right? It just sits there. Press it, it exerts a force to try to get back to its relaxed length. And if you stretch it, it exerts a force in the other direction to try to get back to its relaxed length. So qualitatively, the force by a spring is proportional to its stretch. Now, what's stretch? Well, stretch is just the difference between current length and relaxed length. So, so we could write the magnitude of the force exerted by a spring is equal to the stretch times some constant. What's the constant? We use the symbol K sub s. This is called the spring stiffness, or some people just call it the spring constant. It just has to do with how stiff the spring is. So the stiffer the spring, the harder you have to push to compress it, the bigger a force it exerts back on your hand. Okay. And absolute value. Why absolute value? Well, how do we calculate stretch? So if the relaxed length is we're going to call it L0, and the length now we'll just call L, then stretch is equal to L minus L0. Now notice that if we pull on the spring and make it longer, so it was 10 centimeters long, its relaxed length, but we pull on it, we make it 20 centimeters long, what's the stretch? Yeah, so if L0 is 0.1 meters, L is 0.2 meters, so the stretch is 0.2 meters minus 0.1 meter is 0.1 meter. Okay, what if we compress it though? So L0 is still that, but now we have is meters. What's the stretch now?
0.0,
Negative 0.5, right? So it's going to be 0.05 minus 0.1 meter is negative 0.05 meters. So stretch is a sign quantity. It's a scalar. Just one length minus another length. And so if we're interested in the magnitude of the force, we can take an absolute value, because the magnitude is always positive. However, and so the spring stiffness, if this is in newtons and the stretch is in meters, then the spring stiffness must have units of newtons per meter, right? Okay. And we're going to be working with springs in lab, and they have ordinary, I mean, there are very stiff ones and very soft ones, but, you know, 20 newtons per meter is not an unreasonable kind of stiffness. So we see that if we have, so here's our spring with length 0. If L is greater than L0, then stretch is greater than 0, but here's L0, here's L. Stretch is less than 0. Okay, so it's a signed number. However, we really need to add a direction, and so we need to worry about turning this into a vector in just a minute. But let's actually just practice a question about come on. Here we go. Okay, so we have a spring whose stiffness is 30 newtons per meter, and it's 12 centimeters long when it's relaxed. You push on the spring, compressing it, so its length is now 10 centimeters. What's the stretch? You're all really quiet again. Okay, so fingers. Awesome. Okay, so everybody gets it. The answer is 4. It's negative 0.02 meters. Good. So the same spring. What's the magnitude of the force the spring now exerts on your hand? Okay, if you're not going to talk, show me your answer. All right, that's why you're not talking. Okay, so the answer is 1. We're just using this equation, right? So we have the magnitude of the force is 30 newtons per meter times the stretch, which is a minus 0.02 meters, but we want an absolute value because it's a magnitude, and so we get 0.6 newtons. Okay, so nothing to it, right? But we need to write the force as a vector because the direction of the force, it's always going to be along the length of the spring, but where the spring goes might be a problem. So if we have a spring that's sitting vertically and we push down on it, so here's our hand. That's our hand in a mitten. So the force exerted by the spring on our hand is going to be that way, but if we take the same spring and we pull up on it, stretching it, then the spring is going to pull down. And suppose we had a spring that was stretched at an angle, then the force, so we're stretching it with our hand, then the force on the hand is going to be like that, so we need a way to find a direction. Okay, so that means vectors. And we're going to define a vector L that extends from where the spring is anchored to something to the movable end. So if we have a spring that's sitting upright on the ground, then this, so I'm just going to draw it here. Goes that way. Now what if a spring doesn't have a movable end? You know, it's got two free ends. Well, consider one end, you know, take the end you're not interested in, the end that's not exerting the force that you care about, that's the fixed end, and the other end's the movable end. Okay, so so if a spring is hanging from the ceiling, what's the vector L there? So it starts there and goes there, right? Because this is typically the end that's going to have a block on it or something, and we're interested in the force that the spring's going to exert on that object. So, so in this vector L, what's the magnitude of L? That's how you calculate it, is the sum of the squares. But what is the meaning of the magnitude of L here? Is that related to some quantity we were using before? It's just the length of the spring, right? Okay, so the magnitude of this vector L is so what are the units of L? Meters. So now we can redefine our stretch a little bit as so L is a vector from fixed end to the movable end, or the end and so the stretch is now the magnitude of L minus the relaxed length. Okay? So let's see if we can convert the equation we have into an equation that actually involves a vector and therefore has a direction. So let's consider two different cases and see if we can generalize from those. So here is our spring. It's vertical. This is its relaxed length. We push down on it. So the spring is going to be exerting an upward force on our hand, right? So we need our force come out upwards. So let's say that the spring force, how do we get a vector that ends up having, it's got the spring stiffness, it's got the stretch, and it's got something here that turns it into a vector. So let's see, the direction of the vector L is up. But we've actually already taken care of the magnitude of L in this S piece here, so we don't want the magnitude of L to come in again. So what's a vector that gives us the direction of L without changing the magnitude of anything? The unit vector L hat, right? So the unit vector here's our vector L, and so our vector L hat is in that direction, so L hat is up. Now let's multiply L hat times the stretch. Is the stretch positive or negative here? Stretch is negative, so the quantity L hat times the stretch is actually going to point down, which is not the direction we want for the force, so we better add a minus sign. And so if we have minus L hat S, that points up. And so it looks like we can write this equation as a minus K sub S times L hat, and that should actually give us the right magnitude and the right direction for this force. So let's check it for another situation and see if that really works. So here's a spring with some relaxed length, and now we stretch it. So the direction of the force needs to be up. So what is the direction of the vector L in this case? Yeah, down, so negative y. So we have L is down, so L hat is also down. Is the stretch positive or negative? Positive, so S greater than 0. So S times L also down. And so minus S times L hat is up. So minus a positive constant times S times L hat gives us the right answer. So that looks like a vector equation for the force. So here's our full equation for the force by a spring. Negative sign, this spring stiffness, which is positive number, the stretch, which is calculated this way, and the unit vector L hat. Now, in many situations, L hat you can get by inspection, right? So what is the vector L hat numerically in this case?
0, 1, 0.
Everybody. Yeah, 0, 1, 0 is pointing up, so it's only got a y component. And so somebody else, what's the vector L hat in this case? Yeah, so L hat is 0, negative 1, 0, okay. So a lot of the time, this isn't terribly problematic. Questions? Okay, let's just calculate one. So, we have a hanging spring, and its relaxed length is 10 centimeters. We attach a block to it. We pull it down and let it go so that it oscillates up and down. And at a particular instant, the length of the spring is 14 centimeters. So if the spring stiffness of this particular string is 20 newtons per meter, and so So let's find, we really want to find the spring force, and in order to do that, what other quantities do we need to calculate? Stretch. L hat. Okay, so take a minute and see if you can do that. So what's the answer? Well, 0.8 is not a vector.
Or 0.8.
So you're asserting that it's the vector 0, 0.8, 0 newtons. Do you agree? Mostly yes. Okay, so how do we get the stretch? So what's the vector L in this case?
-0,
Okay, so L is actually 15 centimeters long, and it's in the minus y direction, so it's 0 minus 0.140 meters. What's L hat? Yep. 0, -1, 0. The stretch was positive 0.04 meters. And we multiply by the spring stiffness and we get the, okay. So not that much to it. Is this force that we calculated, is that the net force on this block? No, why not? What other forces are acting on the block? Gravity. So the Earth is interacting with the block too. So we actually have two forces. We have the spring pulling up. We have force due to the Earth pulling down. This force isn't changing, but this one is, and we get some interesting motion. So let's at different points in this motion. So we've got a block, there's a spring, so a block sitting on top of a spring. And we push it down, hold it there to make sure it's not moving, and then just move our hand off so we don't add any extra impulse with our hand. At that instant, since we've had to push it down, what's the direction of the net force on the block, and what's the direction the block's momentum will be in the next little time, 1/10 of a second? So the block's sitting there on the spring, then we push it down, hold it there for a moment, release it. What's it? Okay, so what's going to happen in that next tenth of a second, hundredth of a second? Okay, talk to your neighbors. Which one of these is correct? Okay, so I'm hearing at least some people saying that number 5 should be not enough information. So let's make 5 not enough information and show me what you think the answer is. Okay, 0. Okay, so I'm seeing 4s, I'm seeing 5s, I'm seeing... Okay, if you can't answer it, ask a question. If you don't have an answer, ask a question. Can you articulate a question? Okay, so 4 is the right answer, but some people were concerned that they didn't know what the net force was because there are 2 forces acting on the block, the gravitational force and the spring force, and you couldn't tell which one was bigger. But let's think about the description of the situation. So we said, here's a block on a spring sitting there, and we push it down. Okay, before we push it down, if it's sitting there, what do we know from the momentum principle? What does the momentum principle tell us about the net force on this block? Must be 0, because in the next fraction of a second the momentum doesn't change. And so if the momentum is 0 and remains 0, then F net delta t must be 0. So in this situation, with at equilibrium, the force by the spring and the force by the earth have to be equal and opposite, right? So F net is 0. But now I push it down. You push it down with your hand. You compress it, which means the downward force to get it there, right? When we remove that downward force, what's the direction of the net force acting on the block? It is. So the net force is going to be up. And in the next delta t, momentum will increase from 0 to some non-zero quantity in the upward direction. So that's what we predict is going to happen in this time. Now, indeed, there. Okay, we'll work this out. Now let's consider a different situation where we also, yes. Yes.
What if pushing it down?
Uh-huh.
Won't the initial velocity be going down?
No, because we push it down and hold it still.
Oh.
Okay, so what we do is we pushed it down and we held it still. So in this situation, we have 3 forces acting on. So here's our hand and our bright green mitten. We have 3 forces acting on the block. So the Earth is pulling down. We are pushing down. the spring is pushing up, and if the block is motionless, we go back to the momentum principle and we say that the net force on the block must at this moment be 0. So these two downward forces have to add up to be equal to this upward force. It's motionless. Now when we take our hand away, we still have the force by the earth, and we have the force by the spring, but we no longer have this force by our hand. We just carefully moved it off. And so now the net force is, it's instantaneously still at rest at that nanosecond, picosecond, attosecond when we've removed our hand, but there's a net upward force. So in the next short time, the force is acting upward to increase its momentum in the upward direction. Okay, that's a good question. Other questions? Okay, one other situation that we, let's consider, so the spring is going to do this. It's going to go, block's going to move up and down. Okay? So when we get almost just before it reaches the highest point it's going to reach, what can we say about the direction of the net force and the direction of the block's momentum? So, so the block is going to get up to here, but right now it isn't quite there yet. Okay, it's gonna get there in the next delta t. It's not quite there yet. What can we say about the directions of its momentum in the next delta t and the net force acting on it? Okay, so it's the it's slowing down, right? So the momentum, what's the direction of momentum at this instant? It's up, isn't it? Okay, so momentum is still up. But when it gets to here, what's its momentum going to be? Right, so momentum is 0 there. And so what do we know about the direction of the net force acting on it during this interval? Got to be down, doesn't it? Got to be down. So F net has to have been down, because 0 vector minus a vector going up is a vector going down. We can do it with numbers. 0, 0, 0, minus 0, 2 in some units, 0 gives us some vector for the net impulse, right? Okay. So what we really want to do is use this iterative procedure to predict the motion. So what we want to do is do that. Get the net force, update the momentum, update the position. It's in a different place now. So which things do we have to recalculate every time through this iteration? A minute. Okay, so what do you think? Wow. Okay, awesome. Yeah, you're right, it's 2. So we need to calculate the stretch of the spring because it changes. The length of the spring keeps changing. We need to calculate, the reason we need it is because we need it to calculate the force the spring is exerting on the block. And the spring force on the block changes because the stretch of the spring changes. The force by the earth on the block, that's a constant, right? So we could recalculate it, but we'd be recalculating a constant, which is okay, but the momentum of the block is changing, the position of the block is changing. We need the position of the block to get the new force, so right? So perfect. You're on a roll. So let's see what this would look like. Okay, so here's our block on a spring. And this is a graph, so it's going to make a graph as we go along. It's going to make a graph of y versus t. Oh, that reminds me. The pre-lab this week, even though we're doing an experiment, the pre-lab was a little trinket on making graphs in BPython. The Monday lab, if you didn't get it done, it's not your fault because I posted it too late. So no penalty for doing it late. Just do it if you're in the Monday lab. But we'll use it next week, so you need it. Okay, so there are going to be 2 arrows here, and we're just going to go step by step. We're going to take steps of 1/10 of a second here. And we're going to use arrows to visualize 2 vectors, the net force on the block and the momentum of the block. So at this moment, this is our situation. So the block is sitting on the spring, but we pressed it, let it go. So the net force is up, just like you said. And so during this delta t, we get a momentum going up, and so the block moves up. Well, now the stretch is different. So we need to recalculate the spring force and add it to the force by the earth. And we see that now it's gone far enough that actually the force by the earth is winning. Or maybe the spring is pulling it down some too. But the momentum is still up, even though it's now going to be smaller. So in the next time step, it still moves up. Now we have a big downward force because the spring is now stretched, so the direction, and the momentum changes in this interval to going down, so the block starts to move down, and now the net force is down, momentum is increasing down, but now the net force is up again, so we have a very tiny momentum. We must be nearly at the bottom. And now we've got a big upward force, and we have a momentum up. And so if we keep downward force, momentum, or big downward force, momentum reverses direction. Downward force, momentum increases. Upward force, momentum decreases, but it's still in the opposite direction. So note that the force and momentum are not necessarily in the same direction. What's in the same direction is the force and the change in momentum over that step. Okay, and so we get something that looks like an oscillation, right? Now that doesn't look like a particularly good graph because the spring doesn't do that. But we took kind of a big time step, so let's see what happens if we make the time step much smaller. So our blue graph looks a lot better. And it's clear that by taking a short time step, we were overestimating forces and overestimating changes in momenta. So things. But this is what computers are good for. They don't get bored. And so we actually get something that looks like a sine curve for y versus t. And it actually is, but the interesting thing is that we didn't put a sine curve into the program. All we put in is the calculation of the spring force, the calculation of the force by the Earth on the object, the momentum principle, position update, and so behavior emerges in interesting ways when we do that position update. Yeah.
Does this mean we could sort of define the sine curve by this function?
Can you define a sine curve by this function? Actually, yeah. You could. And we'll see in chapter 4, we'll get around to actually taking an instantaneous version of the momentum principle, and we'll see that we can solve a differential equation and get a sine curve out for the case of an ideal spring. Now, if your spring isn't an ideal spring, again, we're back to needing to do it numerically, but other questions? Yes, Jonathan.
So basically, the force of the string points towards like where the relaxed point is. So like if it's stretched too high, it points down, or if it's stretched too low, it points up.
Yeah. It always the spring force acts to restore the spring to its relaxed length, right? Yeah.
Is there a sheet somewhere where we can like see how to like write this on a Python or like GlowScript or something?
We will do this in lab, but let's actually just kind of talk about what it would look like for a minute. So the question is, could we see somewhere how to do this in VPython? So GlowScript is just an environment where you write VPython code. Trinket is another environment where you write VPython code. You're always working in VPython here. So let's just kind of sketch out what this program would look like. So we make some sort of a block, which is a box, and it's got position and stuff like that, right? And we probably want to represent the spring by a helix. So how does a helix work in VPython? Well, you saw actually in the spider program, if you looked at the twig, that cylinders are, that even though a box has its position at the center and a sphere has its position at its center, a cylinder has its position at one end, and then there's a vector that goes from that end to the other end that's called axis. So we had, for our twig, we had twig dot position pointed to that end, and then twig dot axis referred to the vector from there to the other end. So that this location was twig dot position plus twig dot axis. I know that some of you actually got it done that way. So we set up all this stuff, and we define a spring stiffness and some other stuff. But what goes in our while loop? T is less than some T final. Well, you just told me what had to be in the loop. So we have to calculate, to get the stretch, we've got to get the vector L. So that would be the position of the block minus, so helix works the same way as a cylinder does. So a helix has a position and an axis. So this would be the spring position. So that would be our vector L. And because the block is moving, we need this calculation inside the loop. So we can't write it that way. We're going to have to write that. It would be really nice if we could put vector symbols on quantities in Python, but we can't. And so now we can calculate the stretch as the magnitude of L minus L0, which we defined up here somewhere. And now the spring force is just going to be, where's our spring equation? I erased it. Let's put it back. So it's just going to be minus K sub S times S times L hat. And now we're going to need the net force, so we're going to have to say F net is F spring plus the gravitational force. And so we have two choices. We can either just recalculate the gravitational force inside our loop, or we could put it before the loop because it doesn't change. So let's say F grav is a vector 0 minus mass times g, both of which we defined up here somewhere. And now the momentum of the block is the block's momentum plus F net times delta t. Momentum principle. And block position plus our approximation P times dt do it again. Now there's a cosmetic thing we probably want to do here, which is we want to make the spring actually stay connected to the block, and it's not going to do that automatically. So we could put here, we could put spring dot axis equals L here to keep updating the spring axis. But that's the program, and it's just the calculations you would do on paper, except translated into the Python. Other questions? So we could post a little you want me to program like this in Canvas? Okay, I'll do that. So, so the spring force is a force that changes. It changes with the stretch of the spring, right? And so we can't treat it the same way. We have to treat we treat constant forces, because since it's changing, we can't just multiply by some long time interval and get momentum change. We have to break it up into much smaller time intervals. And what we're doing here, you probably figured out, is what's called numerical integration. So we're adding up lots of changes over lots of little delta p's over a long time. And so what we're getting is the integral of dp, basically, over this. And if we add it to our initial momentum, we're getting the final momentum. But so we're doing it numerically. Why are we doing it numerically? Because in many cases, you can't do it analytically. So here's another force that changes with position. Physicists like to really simplify the world if they can. And so there are lots and lots and lots of kinds of forces. There's a force that if you push down on something, it pushes back. There's spring forces, there's friction forces, but physicists classify all forces as a combination of four very fundamental forces that can't be simplified any further. Well, that's not quite true, because physicists are working really hard to try to somehow make that into one force, and have made some progress. But these fundamental forces are called the gravitational force, which affects anything that has mass. The electric force, which affects anything that has a net electric charge. You know that ordinary matter is made up of protons, electrons, and neutrons, and electrons have arbitrarily been assigned the sign negative, so they have a negative electric charge. Protons are positive, they have a positive electric charge. Protons and electrons attract each other, so anything that has then there's neutrons. So nuclei of atoms are composed of protons and neutrons. Neutrons have no electric charge. But they actually do interact with the protons in the nucleus through a force that's called the strong force. And things that interact through the strong force is anything that we think is made up fundamentally of what we call quarks. Quarks are little particles that are smaller than protons and neutrons. Quarks themselves do have electric charge, and their charges are weird. They're like -1/3 or +2/3, things like that. And so a proton is made of 3 quarks whose charges add up to +1 times 0.6 times 10 to the minus 19 coulombs. A neutron is made of 3 different quarks whose charges add up to 0. And electrons are not made of quarks. They seem to be made of themselves. They're a class of particles called leptons. And there are other particles that are leptons. So they don't interact by the strong force. So things made of quarks and you can tell that this. Why is it called the strong force? Well, because think of an atomic nucleus. Think of a carbon nucleus. It's got 12 protons in it. repel each other. They're all charged electrically positively, and positive charges do not like to be close together. They want to get really far apart. What keeps them in that tiny, tiny, tiny nucleus whose diameter is about 10 to the minus 15th meters? It's the strong force. There's some neutrons there too, and it's the strong force holding the protons and neutrons together that actually overcomes this electric force and keeps these particles together. And finally, there's something called the weak force. And this is one that we don't see very often. We kind of see when things that are interacting by the weak force come apart. So it turns out that a single neutron sitting by itself in the air doesn't last very long. It only lasts about 15 minutes or so, and then it'll decay into a proton and electron and antineutrino. And what was holding that all together was the weak force, so it needs to be stabilized by other things. So these fundamental forces, so what about the spring force? Well, springs are made of protons and electrons, and as you know, the electron cloud surrounds the outside of the atom is a cloud of electrons. And so these interacting electrons, protons and electrons, billions of them, all interact electrically in such a way that what you end up with when you add up all those little subatomic forces together is the spring force. And we'll talk in chapter 4 a lot more about things like forces that the table exerts and things like that. But for now, let me just give you a taste of what we're going to end up doing next time. We'll talk about the gravitational force. And it turns out once we've talked about the gravitational force and we've written equations for the gravitational force, we can actually model the electric force really easily because its mathematical description is really, really similar to the description of a gravitational force. So we kind of get two for the price of one. So here's the basic idea of a gravitational force. And Isaac Newton, of course, was the first person to realize that this was the case, to understand this really. So if we have two massive objects like the Earth and the Sun, or even two tiny objects like two protons, yes, so they interact the same way. These objects interact with a force that we call a gravitational force, and they're attracted to each other. Gravitational force seems to have only one possible direction. Any massive object attracts another massive object. So the Earth is close enough to the Sun, even though it's not very close, that the Sun exerts a force on the Earth. And the Earth exerts a force on the Sun, actually, that's equal and opposite. It doesn't do as much because the Sun is much more massive than the Earth, so change in momentum of the Sun would mean a small change in velocity because it's got such a big mass, whereas a change in momentum of the Earth would be a much bigger change in velocity, smaller mass. So the direction is toward the other object. And if something's farther away, the force is smaller. So the force depends on distance between these two things. Turns out to depend on the distance between the centers of the two objects. So we can sort of imagine that Superman came along and squashed them both down to little teeny point particles at their centers. That's how they behave. And so we'll call this actually we'll call this the magnitude of R. And since the R vector has to go one way or the other, we'll make R go that way. Is that going to show up in the denominator of the force or the numerator? Denominator, because force gets smaller as that gets bigger. So we're going to have magnitude of R here. How do you think it depends on the mass? Suppose we double the mass of the sun. Will the force get bigger? Or the force on the Earth be bigger? Or yeah, be a lot bigger, right? So where does mass go? Numerator. What about the mass of the Earth? Does it depend on the mass of the Earth? Yeah. So there's some constant, capital G. And it turns out that if you do careful measurements, this depends not on R, but magnitude of R, but the magnitude of R squared. So it falls off really fast, because if you double R, R squared goes up by 4, you get a much bigger number here in the denominator. So that's going to be the magnitude of the gravitational force on the Earth by the sun. What do we do about directions? We need a unit vector. Yay. So our vector, so we're interested in this force. We're interested in the force on the Earth by the sun. Our convention is to draw the vector starting at the sun, the thing that's causing the force, and ending up at the Earth, the thing that's experiencing the force. So that's the vector R. So a unit vector R hat would certainly point that way. That's the wrong direction for our force. So we end up with a gravitational force looking like this. We have a G, which is a constant. We have the magnitude of R squared. We have R hat, and then we have a minus sign to make the force come out right. And we'll explore this force and see what we can do with it. Okay, in recitation, we're going to do problems involving springs. Good work today. You guys are really on.